questions about your homework? You had 1 through 12 and then 17 through 20. Anything? 20? 11? Okay, well, I'm going to start with 11 since it comes first. Then I'll go 17, 18, 19, 20, and 12. Okay. So 5 through 12 asked you to use the alternate definition of a derivative, which, what? Oh, okay, so I can use whatever I want. Thank you. All right, so I need to find the derivative of x squared. What did y'all use? The alternate or the difference quotient? The difference quotient? All right, so the limit as h goes to 0 of f of x plus h minus f of x over h. Well, here we go. You don't. So what you want is a general equation. So I'm going to plug x plus h in like this, minus, and then I'm just going to keep the x squared, and I'm going to put it over x. Plug it in for what? All right, so now I got the limit as h goes to 0. This is x squared plus 2xh plus h squared minus x squared over h. Lucky for us, as it should. The x squareds are going to cancel so that then I can take out 1h from everything, and I am back to the limit as h approaches 0 of 2x plus h. Now I can put a 0 in for h, and I can find out that, in fact, the derivative of f is 2x. Yeah. The equation at the start. This one? Okay, so what we were doing before we were finding the derivative at a specific point, right? And they'd say when x equals whatever it is, blah, and we'd plug that in for the x, right? But they didn't give us that blah this time. They just said find the derivative. So not the derivative at a point, but the general derivative. So what we did was we left the x in there. Instead of doing 2 plus h, if it was x equals 2, let's say it was 2 here, I would do this, right? But instead of doing that, I just left the h there and did it the same way. I plugged in, instead of 2 plus h, I left the x plus h squared, because it's just x squared, minus, and then the function itself, which was x squared. That just means take the derivative. And the derivative is the difference quotient. If you ever see this, this is difference quotient, or you can use the alternate definition. And now the nice thing about this is more work, but I could take this equation and I could find the derivative at any point. So now I could say, what's the derivative at 2? Well, the derivative at 2 would be 4. Or what's the derivative at 10? Well, the derivative at 10 would be 20. I could just plug those values in now instead of in the beginning. Does that make sense? No. So this says, what's the derivative, which means slope of the tan line, right? When x equals 2. By finding this general equation, I could just plug 2 in there. I would get the same thing if I came up to the top and I put 2's in for the x's here. Y'all okay there? Yeah. So would those values not cancel out if you did it? You should, yes. Yes, because unless it's linear, unless the derivative comes out to be linear, which would be, I mean, unless the derivative comes out to be a constant, which would be a linear function, yes, you're correct. You're correct. You would need a different question. I told you I didn't like that alternate. It's not my favorite. But thank you for clarifying that. Did y'all hear that? The alternate is only at a specific point. It's not for a general equation for derivative. All right, and then you said which one, 12? Same deal with 12. Find the derivative. And they're really just writing these in different ways to get you used to that notation. If f of x is 3x squared. Difference question again. So I'm doing the limit as h goes to 0 of f of x plus h minus f of x all over h. I don't have an x to plug in, so I'm leaving it as is. I want the equation of the derivative. So I have the limit as h goes to 0 of 3x plus h squared minus 3x squared. Does that make sense? Now I'm going to multiply it out. X squared plus 2xh plus h squared minus 3x squared all over h. I'm going to write this one out for you before I start slashing and marking out, just to keep you from getting confused. 3x squared plus 6xh plus 3h squared minus 3x squared all over h. My 3x squareds cancel, and now everybody has an h that they can give up, right? Here, here, and here. Which is nice because now I don't have one in the bottom, so I should be able to sub in now 6x plus 3h. Yeah. Did you have a question? Oh, okay. I can put the 0 in and I end up with 6x. So the derivative of f is. So for the alternate, that's what we were talking about just now. It needs to be at a point. The only time you can do, unless you start with a linear function, because the derivative of a linear is a constant. But you really need to be going to a specific point unless it's linear. Y'all okay on that first set, 1 through 12? You sure? All right. How about, you said 17? If f of 2 equals 3 and f prime of 2, what does that mean, f prime of 2? The derivative at 2, which is the slope of the tan line at the point when x equals 2. Okay. Find an equation of the tan line and the normal line to the graph y equals f of x at the point where x equals 2. Well, I know the slope of the tan line, right? When x equals 2. So I have a slope. I also have a point, right? I have that particular point. That point is 2, 3. Okay, so whatever else is going on this graph, this is the point 2, 3, and the slope of this tan, well, that's a terrible place for 2, 3 to be if the slope is 5. This is 2, 3, and the slope of the tan line that comes through this, or intersects at this point right here, is 5. Y'all follow me? So I need the equation of this red line. I have a slope and I have a point. So y minus 3 equals slope. So yes, then whenever you're asking, this is the tan line. So then if you want the normal line, remember all that does is take that slope. It's perpendicular, so it's negative reciprocal. So my slope here would be what? Negative 1/5. Point is still the same because I'm at the same point, but now I'm coming through here perpendicular to the tan line. The same point, just different slope. So y minus 3, negative 1/5, x minus 2. And of course you can move that 3 over. So 18 is a little bit harder, but yes. So you have to use the derivative, either the difference quotient, or you can use the alternate one there since you have the x. You want me to do that one? Oh, did we? Okay. That's okay. I mean, I don't mind doing it again if you want me to do it again. Sure. Okay. If you look at it and still have questions, let me know. 20. Find the lines that are tangent and normal. Ooh. Y equals the square root of x at x equals 4. So it says find the lines that are tangent. Let's do tangent first. How do I find a tangent line? First I need the what? The slope, right? How do I find the slope of the tan line at 4? Difference. I could do difference quotient, or I could do the alternate one here, right? Because the difference this time is I'm at a specific point. So that's the difference in those 11 and 12 we did, where we didn't have a point. This time I have a point. So I could use either one. Do y'all have a preference? I prefer the difference quotient, but if y'all'd rather do. All right, the limit as h goes to 0. Remember, this is just finding my slope. I need a point and a slope. This is going to give me the slope. Yeah. You do. Oh, no, like if you don't have it written here. You have, like, when you write limit as h goes to 0, you can't just put 5 and say that that's the answer. Like, or you can't even do this. Like, you have to, here you have to have an argument with the limit, is what they call it. Not necessarily. What I'm saying is you could go straight into subbing in, right? So the square root of x plus h minus the square root of x over h. You could go straight into that if you wanted to. But you have to have something written here, not just the answer that follows. Some of you on the test were saying you were going through all the work, but then at the end, whenever you found what that slope was, you said the limit as h goes to 0 equals whatever it equals. Well, no, it's the limit as h goes to 0 of, like, you can't drop the argument part, is what I'm saying. Of something equals 5, not of 5. Because the limit, there's nothing written here. It just says the limit as h goes to 0 equals 5. Well, the limit of as h goes to 0 of what? Like, you have to be complete in your, right, yeah. This is where we're continuing to write whenever we work down. Yeah, if it's f of x, if it's the difference quotient, whatever it is, as you simplify it as you go. We'll review it some more. I'll show you whenever we get down. Y'all are stressing about it. Don't stress. It was just to remind you. I'll show you on your test what y'all did. I'll give them back again. Right, or whatever it is you're finding, something needs to be there after the limit, not just what the limit equals, but there needs to be an argument there. Okay. Ooh, gross. What can I do? What did y'all do? Did anybody do anything? Oh, I didn't put the 4 in. Didn't I? Oh, yeah. Shame. Sorry. The other way of what? Oh, you did the alternate? Was it easier? You didn't have to do the conjugate. So I'll do the conjugate here. Multiply top and bottom by conjugate. Try to get something I can work with. Henry says the other way is easier. I'm going to leave that factored because I learned my lesson the last time. Limit as h goes to 0. I've got 4 plus h. 2 times 4 plus h. And if you don't want to write this middle part because you know it cancels, you don't have to. Oh, nope, can't do that yet. Can I? Oh, I'm going to write it so you see it. I can. Because it's just h up top, h over square root of 4 plus h plus 2. So now I got the limit as h goes to 0 of 1 over. Yeah, sorry. I get excited whenever it starts working. And I don't know why, but I have if I had to guess, something with your radicals, you made a careless mistake somewhere. When you foiled it, probably. Now I'm ready to sub in. One over square root of 4 is 2 plus 2 is 4. But I'm not done because I did all that to find the slope of the tan line. So now I have the slope of the tan line when x equals, what was it, 4? Is 1/4. I also need a point. I need the x to be 4, so what is y of 4? So that's the point 2, 4. Oh, sorry, 4, 2. Yeah. Equals 1/4. Yes, yeah, that's fine. Don't come here and say limit as h goes to 0. Don't put the 1/4 here. Or don't say equals 1/4 here, because there's nothing that you're showing that you're taking the limit of. So of course, then I did my equation of the line. 1/4 x minus. You're close. Oh no. And then of course, the normal line would be the negative reciprocal. So the normal line would be y'all good? Anything else from your homework? All right. I will forewarn you, you're going to have to go backwards and forwards on this. We're going to, given the graph of a function, we're going to try to sketch the graph of its derivative without anything but a picture. Okay? It's not going to be quite as hard as what you think it is, but still. So let's say, and I'm gonna explain this to you. We're gonna do one or two together, and then I'm gonna show you a couple clips from Khan Academy because he does a really good job explaining it and sketching it out too. So hopefully by the end of those two, you'll have a little bit of a grasp of it. All right, let's say, and here's what I'm gonna do. I'm gonna do the derivative right below it. So this will be f of x, and then right below we'll come in and do the derivative. So imagine there's a break in between these two. Let's say f of x It's okay. I'm gonna erase this header up here because I need space. Sorry. Sorry. No, that's as high as it's gonna go, but 1, 2, 3, 4. I really wanted this one. 1, 2, 3, 4. Well, this is gonna be 4, -1. I'll put some points on here. So this is 2, 1. Sorry, this point's actually gonna be, sorry, 5, 3. It's off scale. This is a piece of a parabola. Okay. If I graph the derivative, remember what a derivative is. It's what? Slope. Slope of the tan line, right? So let's take these section by section, piece by piece, and let's look at what's going on. Any place I put a tangent on this first segment, do you agree that the slope's going to be the same? We all agree? What is that slope going to be? From here to here, the slope is always what? 0. Because horizontal lines have slope of 0. So anywhere I put a tan line here, the slope's going to be 0. We're in agreement? Okay. So I'm going to come down here on my derivative graph, and I'm going to say, okay, well, from 0 to 2, from 0, and I'm going to do an open dot here at 2, the value is always going to be 0. So this is saying the derivative at 1, well, what's the derivative at 1? Still 0, right? So everywhere between these values, the derivative, or the slope, is 0. Does that make sense? Anywhere in this interval here, the slope of the tan line is going to be 0. So at 1, which is right here, it's still going to be 0. Anywhere I go, that value is going to be 0. F prime of 1. I was just saying F prime. Anything there, if I did F prime of 1/2, it's still going to be 0, because anywhere on this horizontal line, the slope is 0. Are y'all okay there? All right, let's move on to the next little piece. Tell me what you notice about a tan line here. It's got a constant slope. It's a line, right? Anywhere you go on a line and you put a point, the slope's going to be the same. Do you agree? Okay, so we're kind of learning something here, even though you don't realize it. Lines have a constant slope. So in calculus terms, that means the derivative at any point of a line is always the same, right? Because the derivative is the slope. So between 2 and 4, what's the slope going to be? And how are you doing that? That's just your basic rise over run, right? 1 minus negative 1 over 2 minus 4. Always negative 1. Between 2 and 4, always negative 1. No questions asked. Do we agree? Well, then I'm going to come down to negative 1, and I'm going to say between 2 and 4, notice it looks the same, it's just a different value. No, we're going to be open at all the points, and we'll talk about why soon enough, but we're not differentiable at those points. 0 we're going to include. We include the very end points, but not inside. Not where those pieces connect. All right, you try the next little piece. See what you think it'll be and where it goes. Is it constant? Yes, it's constant because it's linear, right? Can we see that? Bless you. What's the slope? 4. 1, 2, 3. Oh dear, that's okay. So from 4 to 5, I have a slope of 4. Agree or disagree? How about this piece of parabola? let's think about these tan lines for just a second. Let me pick a couple points on here. Tell me what's going on with the slopes. From here to here, it is, okay, so left side we know is negative. We agree? Is it more negative or less negative as you move towards the vertex? So this is, and this looks like it could be maybe about -1, but that's going to be less than -1, right? It's getting steeper and steeper and steeper as it heads towards. Does that make sense? The closer I get this way, if you think about a parabola, the more I move away from that vertex, the steeper my slope is getting on a tan line. It's no, I mean, it's getting closer and closer to straight up and down, which would be right. Okay, so if this is approaching -1, tell me what's happening here. 0. Right? Do you see that? Just a touch in that one point at the vertex is 0. Well, that's pretty easy to plot. 0's right here. But then if I look, same thing's happening here, right? Ugh. I'm telling you, Khan Academy does a really good job. That's why I want you to see that. I'm getting steeper as I move out. So the slope at the vertex is 0. So that's the first thing I'd plot. And then I'd look and I'd go, well, but you know, on either side, really, it's looking like it's coming kind of close to 1, right? And then it's getting, this is just going to be bigger than 1, right? So what I'm going to do, I'm going to come kind of in between. So you have to kind of use an estimate on these if you can't figure out what that slope exactly is, especially when we get to quadratics and bigger. Go ahead, ask me. The 0? Okay, so the x's line up the same, okay? And then I'm plotting their slopes. The y value is the slope. It's going to be closed because we're going to do this whole parabola as one. Okay, so think about what's happening. As I'm moving this way, my slope is decreasing, right? You agree? But it's getting bigger, so it's kind of doing this number, and I'm trying to get right here. I've crossed over to 1, maybe somewhere around right here, but it needs to be an open dot. Go ahead. What you mean? The dot at the bottom. Well, this is -1, so it's kind of down a little bit because this is more, right? So maybe somewhere like that. This one again above it also because it's increasing. And the point that I'm getting to here, and I know I'm doing a terrible job with the quadratic part, that's why I'm going to show you this little video. The point that I'm getting to here is that the slope is increasing at a constant rate. Okay, so we said that if I have a line, it has a constant slope, right? Well, the slope of a quadratic is always going to be linear, is what I'm getting to. So let me show you this little video, and then we'll do another one together that hopefully it'll pull everything together a little better. I might need to play it. Can y'all hear that okay? Let me to pause it. What? Let me play it through mine. Because that's as loud as this one goes.
So I've got this crazy discontinuous function here, which we'll call f of x. And my goal is to try to draw its derivative right over here. So what I need to think about is the slope of the tangent line, or the slope at each point in this curve, and then try my best to draw that slope. So let's try to tackle it. So right over here at this point, the slope is positive, and actually it's a good bit positive. And then as we get larger and larger x's, the slope is still positive, but it's less positive. It's less positive. And all the way up to this point right over here, where it becomes 0. So let's see how I could draw that over here. So over here, we know that the slope must be equal to 0 right over here. Remember, over here, I'm going to try to draw y is equal to f prime of x. And I'm going to assume that this is some type of a parabola, and you'll learn shortly why I have to make that assumption. But let's say that, so let's see, here the slope is quite positive. So let's say the slope is right over here. And then it gets less and less and less positive. And I'll assume it does it in a linear fashion. That's why I have to assume that it's some type of a parabola. So it gets less and less and less positive. Notice, here the slope, here for example, the slope is still positive. And so when you look at the derivative, the slope is still a positive value. But as we get larger and larger x's up to this point, the slope is getting less and less positive all the way to 0. And then the slope is getting more and more negative. And at this point, it seems like the slope is just as negative as it was positive there. So at this point right over here, the slope is just as negative as it was positive right over there. Seems like this would be a reasonable view of the slope of the tangent line over this interval. Now let's think about as we get to this point. Here, the slope seems constant. Our slope is a constant positive value. So once again, our slope here is a constant positive value. Let me be careful here, because at this point our slope won't really be defined. Because our slope, you could draw multiple tangent lines at this little point, this little pointy point. So let me just draw a circle. Let me draw a circle right over there. But then as we get right over here, the slope seems to be positive. So let's draw that. The slope seems to be positive, and although it's not as positive as it was there, so the slope looks like it is. I'm just trying to eyeball it. So the slope is a constant positive this entire time. We have a line with a constant positive slope. So it might look something like this. Let me make it clear what interval. Let me make it clear what interval I'm talking about. I want these things to match up. Let me do my best. So this matches up. This matches up to that. This matches up over here. And we just said we have a constant positive slope. So let's say it looks something like that over this interval. And then we look at this point right over here. So right at this point, our slope is going to be undefined. There's no way that you could find the slope over this point of discontinuity. But then when we go over here, even though the value of our function has gone down, we still have a constant positive slope. In fact, the slope of this line looks identical to the slope of this line. We did that in a different color. The slope of this line looks identical. So we're going to continue at that same slope. It was undefined at that point, but we're going to continue at that same slope. We're going to continue at that same slope. And once again, it's undefined here, this point of discontinuity. So the slope will look something like that. And then we go up here, the value of the function goes up, but now the function is flat. So the slope over that interval is 0. The slope over this interval right over here is 0. So we could say the slope over that interval, let me make it clear what interval I'm talking about. The slope over this interval is 0. And then finally, in this last section, the slope, do this in orange. In this last section, the slope becomes negative, but it's a constant negative. It's a constant negative, and it seems actually a little bit more negative than these were positive. So I would draw it right over there. So it's a weird looking function, but the whole point of this video is to give you an intuition for thinking about what the slope of this function might look like at any point. And by doing so, we have essentially drawn the derivative over that interval.
But he still does a good job without it. I think. Clearly
In the
did
last
not.
video, we looked at a function and tried to draw its derivative. Now in this video, we're going to look at a function and try to draw its
Where is it?
antiderivative, which sounds like a very fancy word, but it's just saying the antiderivative of a function is a function whose derivative is that function. So for example, if we have f of x.
Yes, ask me. I'm sorry.
So, like, it makes sense, like, the lines make sense, but I don't understand why the parabola was, like,
Okay, you don't understand why the parabola was negative? So the whole parabola wasn't negative. But this side, so think about, and it depends on which way your parabola is opening up, right? It's not very good. You've got this vertex here. Let's just pick a couple points. If I were to come in and draw the tan lines, right? And tangent lines, remember, just intersect one time. So if I came in to do these tangent lines, so just look at the black line. Compare this one to this one. If that was just a line graph and the red was not even there, right? Think about what that slope looks like. So that's a pretty steep slope, right? That slope might be, I don't know, on a standard parabola, a parent graph, you go over one, up one to get here. This first point is generally would have a slope somewhere around 1. And then over 1, up 1. If this is just the parent graph. Think about the line being, think about the line without the parabola there, the tangent line, and compare the two of them. Okay, so this one as compared to this one. If I called this slope 1, -1, I'm sorry, right? Because it's going down. If you think about rise over run, it looks like a downhill. If I just told you that, you would tell me, well, I know the slope of that is negative, right? Same thing here, it's negative. Here, it's a steeper slope, but we're still negative, right? So maybe if this was -1, this might be, I don't know, -3. It's steeper, it's more negative as I move up away from that vertex. And same thing on this side. If I called this 1, well, as I move further and further up, you see how much steeper that line is. This one looks like it's doing this. This one looks like it's doing more like that. It's steeper. So if this is 1, I might call this, whatever, these are, remember, the parabolas are symmetric. So the slope directly across from it is going to be the same. It's just going to be the opposite sign. So this might be 3. And the vertex is always going to be 0. And we'll learn about those, but maxes and mins on functions are always 0 slopes. Okay. Okay, so this time, slope is still 0, right? As I move, is that, oh, did I draw it the same way again? I did. I'm looking at this picture thinking, okay. Now, as I move over, same thing. Look at the green lines here. This time on this side, it's positive, right? So if this is a 1, this might be a 3. And I'm just estimating and guessing what it might be, but just to show you the difference in the steepness there and how. But if I come to this side, terrible parabola, so it's not quite as obvious. But if I come to this side, my slopes go from like this to like this as I round the parabola. So they get steeper and steeper. But on this side, they're negative, right? Because if I draw that line, that's got a negative slope. So the derivative on one going upside down if I started around 3, here's where it's crossing over because it's 0, and then down to -3. Whereas over here, if I'm graphing the derivative of this one, I start around -3. Here's my 0, and I go up the same amount. So that's the difference in the graphs there of what they look like. Does that make sense? If we look at it, here's a conclusion you can draw. This might help you some too, a little bit in words. If your function is increasing, that means as you move left to right, you're going up. Then your derivative will be positive. Does that make sense? If I am talking about a parabola, no matter which way it's opening, I'm increasing on this side, agree? That means on this side, my derivative will be positive because all the slopes of all the tan lines will be positive there. Does that make sense? If you're talking about a parabola, you're going to have to kind of estimate. But notice, you see how he was saying it's just as positive as it was negative to start with because it's symmetric. And he didn't really say about the symmetry of it. But here, the slope of this is going to be the same as the slope of this. It's just going to be negative, directly across from it. All right, so in the same breath, if f is decreasing, what's going to happen to the slope or the derivative? Less than, it's negative. And if f of x is neither decreasing or increasing, okay, so when is it neither increasing or decreasing? It's flat or it's a turning point. Turning points happen at maxes and mins, right? I stop increasing and start decreasing. That point where that happens, that's when my derivative is 0. I'm going to put here think, max, min, vertex, things like that. Are y'all okay? Maybe, maybe not. Let's see. Let me go to your homework. I want one for you to try. I'm going to put this with the camera because I'm not going to be able to draw it accurately. And we may come back and do this problem following the directions on here. But for right now, I want you to look at this and see if you can sketch the graph of the derivative. Oh, shame. It helps if I plug it in. So that you can estimate slope and stuff. They wanted you to have the points. So, like, they're just saying this is 1, 1, 1, 2, so that if you need the values, you can see what they are. But what? Remember what you know. Increasing, decreasing, turning points. Y'all don't know what to do? All right, let's do it together then. I am just going to So now what I want to do is I want to start kind of estimating some values here. Where I always start is where it's 0 because those are the easiest to estimate, right? I know here, oh, where'd it go? Okay, I'll try not to let my arm touch it. Here, I have a slope of 0, right? Maxes and mins, that's where it's happening. That's where I'm going to be 0. Oh, I didn't realize that was, you do. I just want it to be the exact, you pretty much want the exact same grid there that you have, okay? Yeah, but I don't care about the y value there. So it looks like it's at 1. I'm going to cross then at 1 and -2. And again, this is a sketch. It doesn't have to be exact. Do we all see where those 2 points came from? If my axis was... All right. Okay. When I'm increasing, I'm positive. When I'm decreasing, I'm negative. Okay. So all of this is increasing. Do you agree? So for all of these, my slope is going to be positive, right? So that means I'm up here. Y'all okay there? And then for here, between these two values, my slope is negative. And then from here, my slope would be again positive. Are we okay there? What in the world am I going to do? Well, let's look at the left. What's happening? Am I getting bigger as I go this way, or am I getting smaller? The slope of the line. Think about the slope of the tan line here. It's kind of flattening out, right? I'm getting closer to zero. So even though I'm positive, I'm decreasing and I'm getting closer to zero. Agree or disagree? Okay. I'm just going to, remember this is just a sketch. I don't want it to be quite as constant because it's not really constant, but it's getting closer and closer to zero at maybe not as quick a rate, right? Maybe it's something like curved slightly, just slightly, because it's not, it doesn't matter. I'm not going to do specific values here. I'm just sketching to try to see if I can get what the shape is going to look like. I'm trying to get you to see what, there's a point to this, I promise. It's just not linear. It's slightly curved. It's not, this slope is not getting, it's not so big here. It's not decreasing at a steady rate, it doesn't look like, because of the way that it's kind of curved out. Think about the way like a parabola curves out. How it almost, if you were just to take that leg of it, it looks almost linear, but it's not. It's got a slight curve to it. Now, what's happening here? I'm going from between these two zeros, right? And I'm always negative, so I'm always down here. But watch the slope. So I'm 0. I'm still a negative slope, but it's getting steeper and steeper and steeper. Where does it stop getting quite as steep? Okay, so right in the middle, right? Do you see that? It kind of stops getting quite as steep. Right here is the steepest it'll ever be. Agree or disagree? So this is the biggest negative, if that makes sense. Do you agree? So that's the lowest this graph will go. Does that make sense to you? It's right here on, right around there, I would say. Do you see why? That's the steepest that line goes. Then it starts evening back out to 0. So if it's the steepest, so it's going to go down. We're going to say that's where, about right here. So if that's the lowest it goes, and then it starts heading back to 0, it gets to here, and then it slightly turns back around, and it starts going back up to 0. Does that make sense? Yes, because these are not pieces. This is a continuous graph that's just, I'm just using some points to help me find what's going on. And then on this side, the same thing's happening. My slope's getting bigger, right? But this time it is getting steeper as I move to the right. It's moving away from 0. It's getting steeper and steeper and steeper as I go. So it looks like it's doing the same thing over here, but just in the other direction. Huh. What does it look like? A parabola. Do y'all see how I did that though? It's hard. It's hard to sketch the graphs. I think we'll save the derivative to function for tomorrow. Because I also have to show you how to start with this one and then get to this one. It's a little bit harder. We'll do it tomorrow. Don't get overwhelmed with this. I'm only going to give you 3 or 4. 3, because we just did one together. This is 22. Here's what I want you to try. I want you to try on page 112. So that was 22. We did that one. 24. Actually, start with these are matching. they give you they give you 4 graphs and then 4 graphs of what could possibly be derivatives. So you just match. Those are just A, B, C, D. 24, you're actually going to sketch a graph. 25 and 26. Matching. Don't get bogged down in it. Don't get overwhelmed with these. But hopefully 13 through 16 will walk you into that. Unless y'all want to do 13 through 16 together now. No? Okay. You ready for me to shut up?